All right, let's do some more with these radicals. Let's do another example. Here's an example where they say to, I think they just say simplify. All right, so here's an example. Square root of p to the fourth. All right, here's a time when they give it to you as a radical, and it might be easier to work with if you change it into an exponent, a fractional exponent. All right, so let's see what we can do with this. I got p to the fourth. How can I write a square root as an exponent? That's what we went over yesterday.
It would be fourth root of p.
Would it be? Is that a fourth root? What is it? It's not a fourth root. It's a square root. So it's p to the fourth what?
Square.
No. To the 1 over 2. Right, to the 1/2 power. All right? We spent all class period yesterday working on this. The square root means you take it to the 1/2 power. Do you remember we went over those rules yesterday? Watch. The square root of x is what? X to the 1/2. I don't know what else I can do to get you to understand that the square root of x is x to the 1/2. You just have to know that. So when you see a square root, what do? You take what's inside of the square root and you take it to the 1/2 power. Agree? You got to go over it. All right? You just have to go over it. You can't just rely on sitting in class and just listening to it one time. I wish there was a way where you could hear the lesson more than once. If I could figure that out, maybe we'd have something going here, wouldn't we? It's called sarcasm, by the way. Okay, and we've been told we're not supposed to use sarcasm in class, but it's on YouTube for the world to hear. So Mike Simmons, if you're watching this one, it was a great, great sarcasm statement. Okay, anyway, here you go. So what's this? This is going to be x to the what? 1/3. Everybody see that? And if I keep going, let's do a couple more. If it was the fourth root of something, then it would be what? X to the 1/4. It doesn't matter what's inside here. It could be all kinds of stuff in here. But what do? You take everything in there to the 1/4 power. So in this situation, it's not an x, but it's a p to the fourth. But you take everything inside the root, everything inside the radical, and you take it to, in this case, it's a square root, so you take it to the 1/2 power. Now why did that help us? You might be able to do this in your head, because what's the square root? The square root is what times itself is p to the fourth. So just doing that in your head, what do you think? P squared, right? Because p squared times p squared is p to the fourth, correct? All right. But I want you to see it another way also. This is p to the fourth to the 1/2 power. Look, what's the rule now? We know rules for exponents, don't we? What's the rule when I have an exponent being taken to another power? You multiply the exponents. That's right. So it's going to be p, keep the base the same, and you multiply the exponents. Well, it's half of 4. What's half of 4? It's 2. And we get p squared just like we thought we should. Does that make sense? So sometimes if they give you roots, to tell you the truth, most people don't like exponents, or especially fractional exponents, but there are times where it makes it a lot easier to work with when you have an exponent or fractional exponent. Everybody understand that? Okay. I don't know if they'll give you anything outrageous, no. What if you had this? For some reason, these examples I think are straight from the book. I took notes on it, so I'm just looking at my notes, but I think they're in the book. But watch this. If you had this, if you had the fourth root of p to the fourth. Now, again, you might be able to look at it, understand what the fourth root means, and then figure out how to simplify this. It wouldn't be that hard to do. But I want to show you another way, just so you get used to this fractional exponent stuff. So what would this be? This would be p to the fourth to the what? The 1/4 power. Good. Because if you looked at this originally, you'd say the fourth root. That means what times itself 4 times is equal to p to the fourth. So what times itself, times itself, times itself, times itself, right, is equal to p to the fourth? Well, what do you think? If I have 4 of them and it equals p to the fourth, every one of those has to be what? P, right? No? Yes? Okay. All right. If you don't see that, if you can't visualize that, then that's why I'm showing you this right here, because this is a little more straightforward. This is p to the fourth to the 1/4. What's the rule? You keep the base the same, and what do you do with the exponents? Multiply them together. 1/4 of 4, or 4 over 4 is 1, or just p. So the fourth root of p to the fourth is just p. Everybody get that? Okay, let's do another one. So I've got 16 m to the 8th r to the 6th. Again, this is not hard. You might be able to just look at it and do this in your head, and that's fine. But I want to show you what we're going to do here. Let's just do it like this. All that stuff, 16 m to the 8th r to the 6th, is all taken to what? It's a square root, so it's a 1/2 power, right? So let's do this. Now, you could have just done square root of 16. What is the square root of 16? It's just 4, because you could have thought of it as 16 to the 1/2 power, correct? Or you just write 4. What's this? M to the 8th to the 1/2. So you could think, okay, what's the square root of m to the 8th? But some people just, it doesn't click. But this should click, right? It's just a straightforward rule, okay? You don't have to really think too much. It's just what? 8 to the 1, if m to the 8th to the 1/2. What do you do with the exponents? Multiply them together. So what's 1/2 times 8? Half of 8 is what? 4. Okay, so that's m to the 4th, right? What's the r going to be? Half of 6. So it's r cubed, right? And that's what it would be. That's the square root of this thing right here. Again, you might have just been able to look at it and come up with this, but I wanted to show you that for a reason. You okay with that? All right. All right, this is kind of dovetails into what we finished doing yesterday. The stuff we just finished really didn't, but the stuff we did yesterday was. Do you remember this? If you had the square root of AB, remember what you do? You can split them up into individual square roots if it's being multiplied. You can't do that with addition. All right. With addition, you can't separate them. You just add what's inside of there and take the square root of it if you can. But for multiplication, you can do this. You can go the square root of A times the square root of B. Everybody see that? If I had the square root of A over B, same thing, except it's division, right? It's the square root of A over the square root of B. Those are the two main ones I'm going to deal with right now. In fact, I'm really just concentrating on that one right there. So I'm going to ask you to simplify radicals. We had a math meeting of the teachers the other day, and we're talking about Algebra 1. Like, sometimes it depends on the class, how quick they get things. Sometimes you really emphasize this in Algebra 1. I talked about geometry. I don't really have people simplify this too much in geometry just because it is geometry. I'm trying to teach other things, but I probably should emphasize this a little more. It should be emphasized a little more in Algebra 1 than it is. I should emphasize a little bit more in geometry, but in Algebra 2 is where it really shows up, where you have to simplify radicals. You've already had Algebra 2, so you should have had a little taste of this, but now we're really going to make sure you know how to do this, okay? So there should be no excuse on doing these things. So for instance, if I had, let's just do this, the square root of 25. We'll start off very, very easy. That doesn't even have anything to do with this rule right here, but what is the square root of 25? It's just plain old 5. Okay, I just want to make sure we're on the same page on this, okay? But what if you had this? What if you had the square root of 50 and you wanted to simplify that? Can you think of a number times itself that's equal to 50? Like a nice whole number. Is there a nice whole number that if I multiply 25? 25 times 25 is 50?
Nope.
Times itself. Times itself. Okay, there's no nice easy whole number, is there? Okay, 49 there is, right? 7 times 7, okay, but there's not for 50. So we got to figure out a way to simplify this. And when I say simplify this, it's not putting it into a calculator and getting a decimal, because that would be like 7.1 or something, wouldn't it?
Yes.
So what is it? What'd you get?
7.07.
07, yeah, 7.07, which is close to 7.1, okay? How did I know that? It's not because I have every square root memorized. It's because the square root of 49 is very close to the square root of 50, right? So square root of 49 is 7. 50 is just a little bit more, so I just guessed 7.1. All right? I'm no genius. All right? It's just, you just got to think about where those numbers are located. Make sense? So what we're going to do here is I like to do this. I'll show you a couple ways to do this, but I like to figure out what times what is actually equal to 50. Well, there's several things. There's 5 times 10, right? What else is there? There's 25 times 2, 50 times 1, right? There's always that number times 1, so we won't even consider that one, all right? But we'll look at all the other ones, and that's pretty much it, I think, isn't it? I can't think of any others, right? Just 5 times 10 and 25 times 2. Now, you could go 5 times 10, but as soon as you said 25 times 2, I'm thinking, square root of 25 comes out to a nice whole number, doesn't it? So what I'm going to do is I'm going to rewrite this. See, I'm going to write this as, why did it, no, it's just a little slow. Okay, so I'm going to write it as 25 times 2. Do you agree that's 50? Why did I pick 25 and 2 and not 5 and 10? Because I can, that's right. Exactly right. I can take the square root of 25 and it comes out to a nice whole number, doesn't it? That's why I picked 25 times 2 and not 5 times 10. Now there's a way around doing the 5 times 10, I'll show you in a second, but I think it's a lot easier to go 25 times 2. So let's use this rule now. Where does this rule come into play? It comes into play right now. Because look, that's a times b. That's your a and that's your b. What can you do with them? You can split them up into their own square roots. Do you see that? So I can make that the square root of 25, and I can multiply that by the what? Square root of 2. Now we don't keep it like that, of course. What do? We know what the square root of 25 is. We already, right? That's why I did this number right here. That's, what's the square root of 25? Just plain old 5. It's not the square root of 5. A lot of people do that. I've seen it many, many times. It's just the plain old whole number 5. And then multiply that. You can't do anything with the square root of 2, can you? So I just write it square root of 2. That's what the square root of 50 is. If you put that in your calculator, you get 7.07. If you put this in your calculator, guess what you're going to get? Same thing, 7.07, okay? Because it's exactly the same. Look, all the equal signs, all these things are equal to each other, right? So it's the same exact number. It's just a simplified form. Some people look at this and say, well, that looks easier than this. All I got is just one number under a square root. Here, I got two numbers. I got one outside, one inside. That looks more complicated than this. But the thing is, it's kind of like reducing, right? I took it into its simplest form. I took the square root of 25, I made it into a whole number. So the more whole numbers I have, I guess, the simpler it is. Yeah, I wouldn't use the word easier, but we'll say simple, okay? The simpler that it is. You okay with that? All right, let's do another one. What if I had the square root? I tell you what, before I do another one, let me show you another way you could look at this. Remember we said we could go 5 and 10? All right, and that would be perfectly fine. You could do that. Watch. You could go 5 times 10. You would get the same thing. But I want to show you, I like this way better, but you can still do it this way. You can go 5 times 10. Now, can I take the square root of 5 and come out to a nice whole number? Can I take the square root of 10 and come out to a nice whole number? No, I can't. But I could do this. I could take that 10 and break that down even further, couldn't I? So that first 5 is right there. What's 10? 5 times 2, isn't it? You see that? Look what I got. There's my 25, right? Okay? So it really is the same exact thing. So you could do it both ways. If you didn't realize that 25 times 2 is 50, then you could always broken it down like this. All right? I mean, sometimes you get mental blocks, don't you? You know? Oh, I don't care how you do it as long as you come up with the right answer. As long as you come up with 5 squared root of 2. All right? So look at this. You're taking the square root, right? So anytime you have a pair of numbers and it's under a square root, what's that answer? It's just a 5. Okay? Make sense? And then this is the square root of 2, so it's the square root of 2. You get the exact same thing, just a little bit of a different method to get to it, or a different path we took. All right? What about this? What about the square root of 72? Does that come out to a nice, pretty number? No. So what are you going to think? You could go 8 times 9, and that would be okay, because 9, you can take the square root of 9, right? There's something better than 8 times 9. And we'll do 8 times 9 in a second, but think of a better possibility. Maybe this isn't one that just pops in your head. What is it? Okay, 12 and 6, but I can't take the square root of 12, and I can't take the square root of 6. There's another one. I see it. You don't see it? 72? Well, it ends in 36 and 2. Right? Did you know 36 times 2 is 72 off the top of your head?
No.
You did?
I just did it in my head really quick.
All right, 36 times 2 is 72. Okay, I just thought that was one of those things you just have in your head, but apparently not. Okay, so what I do is 36 times 2. Now, why would I pick 36? Because the square root of 36 comes out to a nice whole number, doesn't it? All right, so now this step right here that I'm doing, it's important at first. After a while, you can just look at this, right, and say, oh, I'm taking the square root of 36, which is what? 6. The 2 still inside of there, so I'm just going to put square root of 2. But for right now, since we're first learning this thing, I'm going to write it like this. So it's just 6 square root of 2. Okay, it's not the square root of 6, it's just regular plain old positive 6. Everybody got it? You could do it another way. You could do it several different ways. Okay, I'm not going to go through every single possibility. But what was the first one you said? You said 8 times 9, right? Okay, so let's write that. 8 times 9. You're thinking, oh, yeah, 9. I can take the square root of that. That's a good number to pick. But 8, that's not even, but I can split that up. Take 8 and break that down. 2 times 4, right? Okay, so I've got 2 times 4 times what? Well, I'm just going to keep it 9 because I already know that I can take the square root of 9. Right? So look what I have. I've got the square root of 2, I've got the square root of 4, and I've got the square root of 9. Right, because let's just do this. So this is the square root of 2. What's the square root of 4? It's just plain old 2, isn't it? I'm showing like every single possible step I could possibly show. Okay, a lot of these you could leave out after you get used to it, but I'm just showing you right now how to do every single step. So this is 2, and this is what? 3. They're all being multiplied. Look, 2 times 3 is what? 6, and then you got a square root of 2. Always put the whole number before the square root, and there you go. You get the same exact answer, don't you?
So could it go on 9 times 4 is square root of 36?
Yeah, you could have done that. You could have said that that was a 36 right there.
Still going the same way you did before.
Yeah, see, and yeah, you would have got that, and then it would have been the exact same thing. Like I said, there's all kinds of ways you could approach this, and it would just take forever to go through every single possibility. I like this way better, don't you? But the problem with this is if you don't know in your head, you got to know your numbers. You got to know your multiplication tables, okay? I just see 72, and for some reason, of course, I've been doing math a little bit longer than you have, okay? But I see square root of 7, or I see 72, and automatically I think 36 times 2, all right? And that makes it a lot easier if you could see that. But if you didn't see it, and the only thing that popped into your head was 8 times 9, you could still do it the same exact way. Make sense? All right. Let's do some that are a little bit more involved. All right, here we go. This one's a little bit more complicated. 175. So when I see 175, especially when it ends in a 5, I'm thinking $1.75, aren't you? Think quarters, right? I went to Main Street last night to go to this guy's. He had a little birthday party at this store in Main Street, this little restaurant, and so I parked at a meter, right? It's like a quarter. It's like 12 minutes for a quarter, right? I stuck in like 4 quarters, and it only gave me like 24 minutes. You know, I was like, "Daggone!" So either they got to change their prices on the thing, or they got to fix their machines. They ripped me off anyway. So
Make sure you put 'em in
I think I put in $1.75, right? And I only got like half the time. Yeah, I think I put them in too quick. I should put it in and wait for it to register and then put the other one in. But I'm not used to parking down there, so or at least using the meters.
I can see you
I was mad. I mean, anybody would be mad, right? Ripping you off. So anyway, so actually, I stuck $1.07. I think maybe $1.50. But anyway, I just saw that number and I thought that was pretty close. I took all the quarters I had out of my car. I tried to find every little quarter. And so anyway, when I see $1.75 or 175, I'm thinking quarters, aren't you? So how many quarters would be $1.75? 7 quarters, right? So if I wanted to break this down, why am I thinking quarters? Because 25 times what? 7. Make sense? All right, so that's what I'm thinking. You could just go 5 into this, right? What is 175 divided by 5? What's 175 divided by 5? Quick. 35. Okay, so I didn't have that in my head. I guess I could have figured it out. But and you could go 35, and you could take 35 and break it down into 5 times 7, right? You see that? So you'd still get the 5, and the 7. So if you didn't realize it was 25 times 7, you could do it other ways. So what do we got? We got the square root of 25, and we have the square root of 7. Square root of 25 is 5 times the square root of 7. Easy.
Now, do we have to do that middle step when we get our answer?
On a quiz or a test, I'm only looking at your answer, okay? But I would at least do this. I think that... Yeah, that's probably not that important, but I'm doing it now because I'm teaching you, okay? I'm not just trying to get the answer to the problem. So I would definitely do this step right here, though. I would absolutely do that step. Don't try to go from here to here in your head. All right? Let's do this one. This one's crazy. We've done square roots so far, right? But we can do the same idea with cube roots. Now this one's quite a bit different, but it has the same basic idea to it. Okay. Everybody with me? It's cube roots, right? So you're going to take the cube root of everything in here. So let's think about it. Remember when we did square root? Because if I had square root and I had like a 5 times 5, let's do this, 5 times 5 times 7, right? If it's a square root, what do? I pair them up, right? Every pair comes out to that whole number. What if I had a cube root of 5 times 5 times 5? What do? No, it's cube root. I took 2 because it was square root. If it's cube root, I take 3 of them, right? You see that? So I group them by 3. So every time I have a group of 3, if I'm taking the cube root of it, what's that going to be? It's just going to be a 5. It's just going to be that number. Okay, like we did here. Because really a square root has a 2 out there. You don't see it because we use it so often, but it really has a little 2 out there. Okay, so I group them by pairs. What if I had the 4th root? I would group them by 4s. Okay, you follow me? If I could. So let's think of this. Cube root of 81. So let's take 81 and break it down. What do you got? 9 times 9, right? Is 81? Or what? 3 times 3 times 3 times what? There's 9 and there's 9, right? So what I'm doing is I'm breaking these down as much as I can. This is all under big old cube root. Let's take x to the 5th. Now I'm not going to take it 5 times, but what am I going to do? I want to try to group them into 3s. So if I took x to the 5th and I group it into 3s, so I'd have an x cubed, right? What would I have left over if I group? I'd have an x squared. Does that make sense? I think this is an easy way to do it. What about this? I've got y. Let's do the y. So let's group them into 3s. Group them into 3s. So I have a y to the 3rd. I got another y to the 3rd, right? Because I want to group them into 3s, and then I got another y left over. There's other ways to do this, but I'm just starting off, okay? And then what about z's? Right, so I got z to the 3rd, or z cubed, and another z cubed. Does it make sense? I'm grouping them into groups of 3s, because every group of 3 is just going to come out to that number on the outside of the root. So let's do this. I even like to circle them. So there's one group of 3. What's that going to come out to be? Just a 3 outside of the root. Now I still have a 3 inside of the cube root, don't I? It's got to stay there. There's nothing I can do with that. What about this? There's an x cubed, so what's that going to be out here? Just an x. The x squared's got to stay inside of there. What about this? I got a y cubed. That's going to come out to be what? A y. And I got this y cubed. That's going to come out to be a y. You'll see that's going to be y squared, right? Okay, and that y's got to stay inside the root. What about the z's? That's going to come out to be a z, and this has got to come out to be a z. It's not so hard, is it? Let's find out what's left inside there. We already talked about it already. We got a 3 left inside. What else do we have? An x squared that's left inside of there. And what else? A y that's left inside. Let's clean it up. We're not going to write it 3x, y, y, z, z, are we? We're going to write it 3x, what? Y squared, z squared, and then the square root of 3x squared y. And that would be a simplified version of that. No, it's not too hard at all. As long as you know how to break them up like this, okay, and group them together, and then pull them out front, it's really not that hard. Looks confusing, looks crazy, but it's really not that hard once you take a close look at it.
Final answer, that cannot be equal to one another, right?
Well, it's not equal to, well, this is equal to this.
No, I'm saying that 3x, y squared, and z squared cannot be equal to the thing in the
No, I guess you could. Yeah, because if this was like z to the 8th, yeah, I mean it could. I mean, and if this had another, that makes no difference. I wouldn't even be, don't even be concerned about if the thing on the outside is the same as the thing on the inside. That's not even an issue. Okay, because yeah, it could be, but it's not in this case. All right? Does that make sense? All right. I think that's good enough for today. We'll do a little bit more tomorrow. There's a lot with these radicals and these rules for radicals. Okay?